Everyone, I'm Qingbo from the Electrical and Computer Engineering Department at the University of Utah. My advisor is Professor Darrin and Professor Mastrangelo. Today I will give a talk titled Very High Density Floating Electrode Flexible Sensor Array for High Resolution Measurement of Contact Forces. This is the outline of my talk. I will start with the motivation of our work. Then I will talk about the high-density biomechanical ground reaction sensor array, two-channel electronic sensing system design, and system characterization results. Then I will conclude my work. Flexible tactile measures as multiple applications include robotic grippers, wearable contact sensors, impact sensors, tactile sensors, and ground reaction sensor array. So for here, I will talk about the application of the ground reaction sensor array. Position tracking in GPS-denied environment is critical. Such applications may include firefighting, rescue mission, and military operations. IMU-based position calculation provides an alternative option. However, IMU device has a problem in terms of low accuracy and time drift. With quadratic integration, this low accuracy may accumulate and lead to a large position error. In order to solve this position error, we propose this ground reaction sensor array assisted personal navigation system. A ground reaction sensor array is placed right next to an IMU inside the shoe underneath the heel here. The bottom figure here shows several different phases during human normal working. In the middle stand phase, which is about 200 milliseconds, the velocity of the heel is close to 0 here. The ground reaction sensor array underneath the heel can provide an accurate contact information between the heel to the ground. As shown here, we can see the pressure contour and contour centroids move from time t, as shown in blue, to time t plus delta t, shown in red. So with the contact information, we can determine the zero velocity of the heel, this moment. And with the determined zero velocity information, we can apply a reset to the IMU device so that we can suppress the IMU error. This can lead to a much improved navigation accuracy. This is our design, the high-density ground reaction sensor array. An array size of 71 mm by 72 mm is chosen to match with a human heel size. We decide an array size of 26 by 26, which leads us to a pitch size of about 2.6 mm. The bottom left figure shows a schematic of one sensor node. Each sensor node can measure vertical pressure as well as x-axis and y-axis shear stress. Capacitive sensing scheme is used in the sensor design. The bottom middle figure shows one set of our sensing electrodes. When pressing from the top, the floating electrodes as shown in green position will decrease, which will reduce the gap size between the floating electrodes and the sense-drive electrode. This will result in an increased capacitance between the sense and drive electrodes. When lateral force is applied, the floating electrodes will move left and right, which will change the overlapping area between the floating electrode and the drive electrode. This will also change the capacitance between the sense and drive electrodes. If you notice here, we have a mirror structure for x-axis sensor or y-axis sensor. So when the capacitance, when lateral force is applied, the capacitance of these two halves will change differentially. This will result in a differential capacitance change. For the axis, when pressed from the top, both capacitance will increase, and we will compare with the on-chip program reference capacitor array, which will be talked about later on. The sensor is fabricated with PDMS and copper gold. The bottom right figure shows an electrical model of our sensor node. The sensor can be dynamically configured to realize y-axis shear sensing and z-axis pressure sensing. The minimum detectable velocity of the hill can be estimated as the pitch size over the dynamic range and the processing time. Given a 10-bit dynamic range and 200 milliseconds processing time, we expect a minimum detectable velocity of about 12.7 micrometer per second. This is our ground reaction sensor array fabrication process. We start with 25 micron capton with 4 micron copper. The copper is then being patterned to form the sense and drive electrode. Vias are being drilled to connect with the sense electrode. Second layer copper of 4 micron is then added for backside interconnection. A 25 micron capton layer is then added by heating and rolling to protect the copper interconnect. One thing you need to notice is that during this step, the whole array will be expanded due to the heating and rolling, and this will cause a problem of photolithography alignment, which I will talk about later on. Until this step, we worked with an external foundry using flexible PCB technique to fabricate our ground reaction sensor array. After that, 10 micron PDMS is steam coated in clean room. And 150 nanometer gold is then deposited and patterned to form the floating electrode. This video shows a demonstration of our fabricated ground reaction sensor array. If you can see, it is very flexible, and it has a thickness of about 70 micron. The right figure shows the micrograph of one particular sensor node. Each sensor node has the axis nominal capacitance of about 1.25 picofarad with about 10% maximum capacitance change on the maximum pressure load. And XY axis nominal capacitance is about 0.6 picofarad with about 1% capacitance change on the maximum shear load. This slide shows our custom designed two-channel electronic sensing ASICs that will be interfaced with our ground reaction sensor array. Each channel scans half of the high-density ground reaction sensor array. The sensing max here will connect a particular column, you can call row here, to the CV converter. And the stimulation max will provide the stimulation voltage to a particular column. So with a selected column and row, we can locate a particular sensor on this ground reaction sensor array. The selected sensor will be reached by the CV converter, and the output voltage of the CV converter will be digitized. The digital output signal can reconstruct the pressure profile on top of this ground reaction sensor array. As we previously mentioned, the heating and rolling step will cause the whole array expansion, which will cause photolithography misalignment. As shown here, we expect the floating electrodes, as shown in dark here, cover half of the drive electrodes, which is in yellow color here. But in reality, as you can see, it is the sense electrode is almost fully being exposed. So, as a result, if you can see here, we expect the sensor as shown in blue merge with the sensor in red if the sensor nominal capacitances are consistent. But in reality, they diverge. So in order to solve this problem, before we deposit the floating electrodes, we adjust the mask and you can see here the alignment is has been much improved, and the sensor nominal capacitance are quite consistent. This can reduce the cross-axis coupling significantly, which means there will be minimal cross-couple from vertical pressure to y-axis shear outputs and vice versa. This slide shows the characterization of a particular sensor node. The normal stress of about 320 kilopascal is estimated based on 200 tons of weights on a single foot. As you can see, with the pressure increase at about our bias points, our sensor start to go to close to saturation region. This leads to an increased small signal Young's modulus, or you can call the slope here, and which is also calculated and plotted on the right plot. The increased small signal Young's modulus are demanding an improved sensitivity for the PDMS material and the sensing electronic, so that we can detect more accurate real velocity information at the bias point. After that, the ground reaction sensor array is being tested under a soft ball. An increased pressure that is applied on soft ball will deform the soft ball and results in an enlarged contact area and contact pressure. The high density ground reaction sensor array, the axis upper voltage profile is being plotted under applied normal force of 1.5, 10, 20, and 35 Newton. This video shows a demonstration that when we rolling a soft ball on top of this ground reaction sensor array. As you can see, the pressure contour and contour centroids is moving with the movements of the soft ball. Now you may wonder, how did I calculate the centroids? So here's the answer. The first two equations shows the centroids calculation for x-axis and y-axis. Lx and Ly in the equation are the pitch size along each axis. Nx and Ny are numbers of columns and rows in the high-density ground reaction sensor array. Vxy is the output voltage from each sensor node. The equation can be summarized as the output voltage from each sensor node multiplied by its coordinates and divided by the whole array output voltage. Based on the centroid equation, if we further assume that the interference at each sensor nodes are uncorrelated and consistent, we can derive the centroid uncertainty equation as shown in the bottom two equations. Delta Vxy in this equation is the interference at from each sensor node. The equation can be further simplified as the interference from each sensor node over the output voltage and multiplied by the pitch size. So as you can see, with an improved signal to noise and distortion ratio and reduce the pitch size, we expect an improved performance. After that, we characterize the centroid noise spectrum. As you can see, the centroid noise exhibits first order white noise spectrum. By averaging n samples, we can reduce the centroid noise by a factor of 1 over square root of n and the system bandwidth of 1 over n. This slide shows the pressure contour centroids calculation results. The centroid noise is being calculated by averaging within 20 samples, and we get x and y-axis noise as 8 micron and 18 micron RMS. The centroid velocity resolution can then be calculated as 38 micrometer per second and 89 micrometer per second. The velocity resolution is the vector velocity resolution is about 95 micrometer per second. Finally, we tested the ground reaction sensor array underneath a static hill. The top right figure shows the up voltage profile when we step on top of this ground reaction sensor array. With this up voltage profile, we can calculate the centroid's position along x-axis and the y-axis over these 20 seconds. And the time drift is due to shaking and movements during the capacitation. To be simplified summary, we can get a vector velocity, minimum vector velocity of resolution of 170 micrometer per second. The increased MDV is due to a hill shaking and movement during the capacitation. To conclude, we designed the three-axis.
We're running over time, so let's skip the conclusion.
Okay.
Let's thank the speaker.